Now I want to show you a few things here. This is my direction of travel. I am traveling from A to B. Here is my TIG torch. Notice I am holding the TIG torch perpendicular, and I'll explain the angle of the TIG torch, the effects of oxides in a moment here. But you see, as I progress with the TIG torch, I am depositing metal. This is my deposited metal. So as you can see, I am welding, I am depositing metal, and I am removing the inert gas away from the deposited metal. Once I remove the inert gas, all of this deposited metal right here, the atmosphere now interacts with it. And it's oxidizing. It is no longer protected by the inert gas away from the atmosphere. It will oxidize and it will form an oxide layer. The thickness of the oxide layer depends on the temperature for which this deposited metal is at. You see, this is a chart right here. I have included this in many videos, but as you know, I quite often and quite frequently remove videos all the time. This is a color characterization, color versus oxide thickness. See, the way that you read this chart right here, this is the temperature of the deposited metal that is now allowed to interact with the atmosphere because you removed the inert gas away from the deposited metal. The inert gas is no longer protecting that deposited metal. Therefore, the atmosphere is now allowed to interact. So depending on the temperature of the deposited metal, you now get coloration. Not only that, you get an oxide layer thickness. The thickness of the oxide layer itself increases. Now you see this right here, this is aluminum. Aluminum does not form, it does not have heat tint. There's no colorization. What you end up with, because when you're welding aluminum, as you progress from A to B, as you progress with the weld, you're depositing metal. You are removing the inert gas away from the deposited metal. The atmosphere is interacting with the deposited metal. It is forming an oxide. Your deposited metal with the oxide will be very glossy. Now the oxide layer on aluminum melts at 3700 degrees Fahrenheit. The material underneath that oxide layer melts at about 1200 degrees. I believe it's 1260, around there or something. Now you see this, I'm going to show you a chart from this book here, Metals and How to Weld Them. You see, take a look at this chart right here. There's the hottest point. It's where you're welding right now. You see outside of that weld, it gets a little bit cooler and a little bit cooler. Now look at this chart right here, and I'm going to show you something. Now say I'm welding aluminum, say, some guys will ask, do you walk the cup on aluminum? I'm going to draw something out that will make you kind of come to an answer on your own conclusion. So you see, I am holding my ceramic cup, the inside diameter of my ceramic cup. This, and remember that chart here. You see this right here, this is my weld puddle. Alright, this is the bevels. This is the bevels of the pipe, this is the deposited metal, and this is the outside diameter of my weld puddle. I am holding the TIG torch perpendicular. If you can see that, you see my weld puddle is being protected by the inert gas from the inside diameter of my ceramic cup. This is the hottest point, just like that chart. You see, here's the chart again. This is the hottest point. This is my ceramic cup is protecting this area right here. Now, as we go outside of the ceramic cup here, the further we travel outwards, it gets cooler and cooler and cooler in temperature. But that's the point, is that I'm protecting my deposited metal. I'm protecting my weld puddle away from the atmosphere. I am holding the torch perpendicular. This concludes with oxides. Alright, the first one was holding it perpendicular. See, I got my bevels right here. Here's my bevels. This is the deposited metal. Now I'm holding my torch, I'm walking the cup. You see I'm walking the cup here, you see? Just walking the cup. My TIG torch is angled and I'm walking the cup. Well, my weld puddle is not round anymore, it's elongated. This is a little bit exaggerated actually, a little bit exaggerated, but you know, hopefully somebody will kind of understand that it's a little bit exaggerated. I will extend the tungsten out a little bit here. See if I can just sort of, just give me a second here. I'll see if I can just pull the tungsten out. Alright, you see what I got there now? Now my weld puddle is elongated. So we come over to aluminum and we come over to oxides. You see, now what I'm doing is I'm heating up, I'm oxidizing the metal on the leading edge now. So ahead of my ceramic cup, I'm protecting this area right here. This area right here I am protecting with my inert gas. However, on the leading edge, now I'm oxidizing the metal because I cannot protect. I'm heating up this area right here. I'll show you the chart again. You see, here is the chart again. You see, so now because I'm holding I'm walking the cup, holding more of an extreme angle. I'm heating up ahead of my my leading edge there. I'm heating up the metal ahead, and it is oxidizing. And when it oxidizes, it forms an oxide layer. Now, the problem with forming an oxide layer, especially on aluminum, is that the oxide layer melts at about 3,700 degrees Fahrenheit. So now I'm walking the cup here and I'm welding over that oxide layer that I'm forming now, and now it's going to be brought into my weld puddle, and I'm going to get such things as porosity, because I cannot melt out that oxide layer because it melts at about 3,700 degrees Fahrenheit, and the metal underneath the oxide layer melts at about 1,200 degrees Fahrenheit. Now I'm going to show you a root pass here. You see, I did this weld in 2010. This weld right here, this pipe right here is pretty old. It's about 5 years old, nearly 6 years old. Now, it's rusting a little bit, but that's no big deal. What you're looking at is, you see this run right here? It's all nice and silver. But you see these starts and stops? You see this blue heat tinge here? That's what I'm talking about right here, this blue tinge on all the starts. Okay, now take a look at this. This is my bevels of the pipe. Alright, we got the bevels. I'm doing the root pass. See, this is my root pass. Maybe I'm welding Inconel, alright? So maybe I thin out the start here. See, I have a nice feather's edge to come off of. On my bevels, I have heat tint. Alright, got some heat tint here, got some heat tint here. Back here, I got some heat tint. I cannot have this heat tint in the weld zone. This heat tint here, can I brush it? Is it a light straw color? Is it a light blue? Can I brush this heat tint off? No? Okay, well then I'm going to take maybe a file. I'm going to let me heat input with the file. Okay, maybe the file's not very effective. I can use a grinding disc. Certain metals you cannot use a grinding disc, such as aluminum or titanium, because you'll overheat the material from friction. Therefore, maybe I'm welding ink now, stainless, maybe a carbon or chrome. So I'm going to take maybe a nice thin old zip cut or something thin. I'm just going to barely just kind of touch it. I'm just going to remove the heat tint. Just a little bit heat tint to nice clean sound metal, no coloration. Nice clean silver metal. I remove any heat tint off the bevels themselves. There's no heat tint on the bevels. On the leading edge where I'm going to start welding, there's no heat tint. There's nothing. So when I strike an arc right here and I come into it in my leading edge here and I start commencing with the welding, there is not going to be any more blue tinge internally. It doesn't exist anymore because this heat tint is oxygen. That's all it contains within the molecular structure of an oxide. It contains oxygen. And even if I have my TIG torch with the external shielding gas on the pipe or the plate, and from inside I have internal purge, even if that's maybe say 25 parts per million, 10 parts per million, whatever it is, I have a phenomenal purge internally, I have a phenomenal purge externally. I'm going to get a blue tinge on my start because I did not remove all this oxide. You know, it contains within the molecular structure oxygen. The oxygen is interacting with my metal as it elevates in temperature. It's going to give me a blue tinge. If you remove the heat tint on your starts and stops on your leading edge there and off the bevels, it'll be all silver. There will be no blue heat tinge on your starts and stops. It'll be all nice and silver. Everything will be silver. Alright, now you see this thing right here. This is a Purge Eye 300 free flow. This is a purge monitor. This thing costs about $2,600 for a purge monitor. This thing right here is a handheld purge monitor. This thing reads in percentage. It doesn't read in parts per million, it reads in percentage. This thing reads from the atmosphere. Say it's about 21% oxygen. Okay, it reads in, from the atmosphere down to 0.01%, which is 100 parts per million. Now, I've used this when I was welding 24-inch stainless. That's when I first bought this little device right here. I was welding 24-inch stainless, and I would, every so often, I'd purge the pipe, and I'd come over and I'd take a couple samples. It has a little bulb that you squeeze, and then you squeeze it, and then you release, and it sucks in the atmosphere inside the pipe, and then it gives me a little display on how much oxygen in percentage is inside the pipe. When it gets to a fair amount, okay, well then I can start welding. You see, this is a chart right here. I'm going to show you this here. So we're going to have, you see what this is right here? You see number 1 is 10 parts per million. So we have this much oxygen that's interacting with your metal as it elevates in temperature, or as it is deposited. The atmosphere will interact with it. Alright, so we got 1 parts per million is at 10 parts per million. There isn't very much oxygen. There's minute traces of oxygen. Only 10 parts per million of oxygen is interacting with your metal as it's deposited. And even when it's at elevated temperatures inside the pipe, you have such a minute oxygen that you're not going to have any discoloration. Well, you're going to have a little bit more. We're going to give it now 25 parts per million. Will you make it the most faint of a light straw color? You'll form a little bit of an oxide, but it's not much, not a big deal. We're going to get a little bit of a kind of a yellowy, kind of a goldish color. We're going to go up to 50 parts per million. Well, we got a little bit of light straw color here. You see where the oxygen, the amount of oxygen, 50 parts per million, we have a little bit of oxygen here, and the oxygen is oxidizing. Just interacting with the deposited metal inside the pipe. It's not very much. Okay, well, we're going to go up to about 100 parts per million and then 200 parts per million. So we're now going to get more and more oxygen, and that oxygen is now going to oxidize the metal. And depending on the temperature for which, that's when this chart comes in handy. You see, this is the temperature the metal is at when it starts, when it oxidizes. You'll get certain colors at certain temperatures as interacts with the oxygen.